Welcome back to FRM 120. We're going to keep going through the pneumatic side of our fluid power fundamentals. So far we've talked a little bit about gauge pressure, atmospheric pressure, how we compress the air, what compressed air is, some of its characteristics. So now we're going to move through. I've got a schematic that we're kind of focus on, and it's one that would be typical of a canning machine or a filling machine, whatever the case may be. But it's going to use the same symbols, and you'll see a lot of these if you ever have to troubleshoot or diagnose a piece of equipment, okay, that's run on pneumatics. But we're going to kind of continue to move along, and we're going to have a schematic here. Now, one of the first things you're going to have to have, obviously, in a pneumatic system is compressed air, okay? However, you typically don't see in a schematic, there are no symbols for a compressor, typically. Okay, now some companies will put their compressor, they'll show a round compressor or something like that, but typically what you have is you have some supply port, because a facility will supply the compressed air to the machine. You know, you've got to hook that up and plumb that in yourself. So they usually have a supply port, and it's typically a triangle that shows you where supply air that you're providing enters into their machine and makes all the rest of the components function. Okay, but this is the symbol typically for a compressed air supply source. Now, just like in electricity that we talked about, you have to have conductors. In electricity, the conductors allow the electron flow to move from point A to point B. Okay, well, we still have flow with pneumatics, and we still got to get from point A to point B. And we also use conductors. Now, conductors are typically plastic lines. Sometimes it can be hard pipe, but it's a conduit in which the air molecules can flow. Okay, remember, we're trying to create flow and not pressure, but we're trying to get that flow through these conductors. So we got supply, and the supply air goes through conductors. Okay, and these lines that you see on this drawing, anywhere there's straight lines like that, that's just conductors. Okay. And it shows you how things are piped and plumbed. All right. Now the next, we talked earlier about gauges, and here is the symbol for a gauge on a schematic. And in this particular case, it looks like we've got three, and they're usually labeled something like gauge 1, or in this case it's GAU 01, GAU 02. There's another gauge up here on this valve body, but this is the symbol for a gauge. And you have multiple gauges because you can have multiple pressures within your system. We'll get a little bit further into this, but you got supply pressure coming here, and you've got a regulator that's going to maybe step it down a little bit from what your supply. Say you had 100 psi, but you're only needing 50 pounds per square inch for the system here. So you step it down, sort of like a transformer kind of, and you step it down to say 50 pounds, and then maybe up here this valve body and everything downstream of the valve body only needs 25. So we use multiple gauges because you may have multiple pressures that you have to have things set for. Okay, and so and a lot of times the components or the process will require you to dial in on a particular pressure so that it functions properly and the timing of everything is right with the stroking of cylinders or whatever the case may be. It relies on that pressure and flow to be exact. So you use gauges to dial in your system. Okay. Now, we talked a little bit about atmospheric pressure, gauge pressure, and things like that. And we said that PSI is a measure of the pressure of the air itself above atmospheric. Okay, so we measure PSI. All right, and then we have also a kilopascal. This is used more in Europe. This is in the event, I'm including this in the event that some of your equipment comes from Europe. It quite possibly could come from across the pond, and it may have KPA on some of the gauges. But bar pressure, you see most of that in Europe and in metric systems, but bar and PSI are the ones that you'll see the most in the United States. PSI is by far the choice that they use to measure pressure here in the States, but bar is also used. And you'll see on this gauge here, okay, the PSI, the little PSI is written in black. I hope you can see this, but It's in black, and so the numbers in black on the scale here are reading in PSI. You'll notice the numbers on the inside, they're much lower numbers. They are blue, and I know you can't see this probably, but the word bar is in blue, and so that tells me that what's in blue is in bar, and it's much less on a scale of, say, from 0 to 100 PSI. It goes from about 0 to 7 bar, roughly the equivalent, maybe just a shade more than 100 pounds. But bar is also a unit of measure when it comes to measuring pressure, okay? And this is the conversion scales. You might want to take a look at these here because you might see those again. There's your hint, okay? So in order to convert to kPa, kilopascal to PSI, we simply divide the kPa by 14.5. To get bar to PSI, we multiply bar times 14.5. So for example, if you had, say, 1 bar, you multiply 1 times 14.5, and if you look, 1 is about the 14.5 point right there on this 0 to 20, so it sort of validates that. So that's how you convert bar to PSI, and bar to kPa is simply the bar times 100. In other words, if you take your bar pressure of 1, multiply it by 100, that's your kilopascal scale conversion. Okay, but just to let you know that you'll sometimes see scales with, or gauges with different scales on there. Most of the time in the United States, you're going to see it's going to be PSI and bar. Okay, so anyway, just giving you a little heads up on that, as we've already talked about gauges, and of course we've talked about they can have multiple gauges, and that is the symbol for a gauge that you'll see on schematics. All right, so kind of moving right along, the next thing that we're going to talk about is the pressure regulator, and this is a pressure regulator symbol right here, kind of minus the gauge there. Okay, so this is a pressure regulator, and it looks like you've got a couple of them on this schematic as well. Okay, and this is what one looks like. You'll typically see one that you can have an adjustment. Okay, you'll have your incoming air going to this side of your pressure regulator. Okay, it'll be coming in this way, and we adjust this by screwing this in or out, up or down, tightening or loosening, whatever you want to say, and that will adjust the pressure. That's the amount of pressure that the system will incur after it's passed through the regulator. Okay, and typically you step down. That's kind of like a transformer. You step down that pressure. If you've got 150 pounds of system pressure in your building, okay, and your system only needs, say, 50 pounds, well, obviously you're not going to hit 150 pounds into your machine. Okay, it could damage a lot of components. So blow lines and it can be kind of dangerous. So what we do is we take that 150 pounds that we have in-house and we dial it down, and we actually kind of dial it up to whatever we need. We might stop at about 50 pounds. I'm just using this as theoretical numbers, but we kind of dial it up to about 50 pounds of pressure, and then anything downstream from there is going to be experiencing 50 pounds of pressure. This is our regulator, and again, this is our symbol for our schematic and our regulator. Okay, this is probably the most important component of a system. You probably think, well, what about a shutoff valve, Mike? Well, not quite as important. This is at work all the time. Okay, if you have a problem, you can't get over there to hit that shutoff valve. You know, this, I consider this much more important because you want to maintain a safe regulated pressure downstream from there. It's like I said, no machine damage. You don't want hoses flying off, and it can also cause personal injury. So I consider this probably one of the most important components as your fail-safe, your safety feature. Okay, and this little dotted line, this little hash mark, is pilot pressure. Okay, and the way this works, make sure I'm not skipping something here. Okay, so the way this works is we've got our pressure. We're coming in here from our regulator. Okay, into our regulator with you know, system air, and let's suppose we have it set at, we dial this, our adjustment here to 50 pounds. Now, this symbol right here is a spring, and this arrow tells us that we can vary the pressure of the spring, okay? The spring is going to counteract the pressure of the air, and I'll show you how that works in just a second. But this symbol right here, a little jagged line like that, is a spring symbol, and this arrow going through the middle of it at an angle tells us that it's variable. Okay, that's also in a potentiometer in electrical, when we vary the voltage of a kind of potentiometer, you'll see that arrow as well. So anytime you see this arrow in this, not this one, but in this one, it tells us that we can vary the pressure in our regulator. It's not fixed, which is a good thing, okay? So we bring in our air right here, and we have our pilot pressure, and it's the same pressure on the downstream side here, and it's going in here, and it's kind of opposing the spring pressure in this regulator. So I've got it set up to about 50 pounds. Now, if my system over here for some reason were to experience greater than 50 pounds, okay, this pressure and the pilot pressure is going to force this little spool here inside the regulator. It's going to force it down, okay, and it's going to shut the air supply off the rest of the way downstream. It's going to shut it off, and it's going to shove the air out into the atmosphere. Now, I didn't mention this earlier, but that is another advantage of pneumatics over hydraulics, okay? Anything that we exhaust from a pneumatic system goes out in the atmosphere. It's air, no big deal, okay? Even oxygen, even CO2, it can go out into the atmosphere. However, if it was hydraulic fluid, we can't just puke it out on the floor, so or the ground. So there's another advantage of pneumatics. You don't have to have a sealed system, and you don't have to worry about the environmental impact should there be something go wrong, okay? So this spring pressure, and I can dial this, and now let's suppose I need to jack my pressure up to say 75 pounds. I turn this and I increase my spring pressure, okay? And as I increase my spring pressure, hold it up against this little spool there that allows the transfer of air in and then out of the regulator. This pressure right here is also building up. However, if it gets greater than the 75 pounds that I now have, it's going to push this down. It's going to overcome this 75 pounds of spring pressure. Should this build up to say over 75, it's going to overcome that spring pressure. This is going to push this valve out of the supply air line, and then it's going to allow it to dump to vent, okay? So that keeps our system intact. It keeps us from experiencing too much pressure on the downstream side. You have pipes, like I said, pipes bust open and things like that that are not rated for that type of pressure. But just a simple notation here, these little dash lines on here means that it's regulated with pilot pressure, and pilot pressure is just anything downstream, okay? This is what the next component we have is a hand-operated shut-off valve. Now, it's going to be a little hard to see. I've had to copy it from here, but this little T handle right here gives us the symbol that it says that it's hand-operated as opposed to solenoid. We'll get into the solenoids in a minute. But it's hand-operated, meaning that if I want to shut the pressure to my system down, I go over there and hit this valve and shove this out, and then we break the supply of air going to our system. Okay, that's a hand-operated. And this is what it looks like. And I know this is kind of blurry. I apologize for that. But I wanted to use it off of that drawing and stay kind of consistent. So we have our air supply, not to be confused with these guys, okay? Y'all remember them? All right. So we've got our air supply, and we're coming into our shutoff valve, and as long as we have our shutoff valve open and everything's fine, then we got air passing through our valve down to our downstream circuit. By downstream circuit, sorry, those guys again, I'm talking about everything downstream of here. Everything is downstream, okay? So that's our downstream circuit. Everything's running along just fine. Now, and then there you go. There, should use that slide there. But we now decided we're going to shut the air off. We press this valve down, and now the incoming air supply is no longer, it has no path to go to because we've moved the spool inside this valve, and it takes the valve and and the new path is shut, the path of the air is shut off, but we still have this pressure in our downstream circuit. It's still built up. We've shut it off from more air coming in, but we've kind of captured all the air downstream. So we've got to relieve that pressure. So what we do when we shut off that valve, it's now creating a port for all the downstream pressure to come back out and go out into the atmosphere. We're exhausting it out into the atmosphere, okay? And we're going to exhaust it into the atmosphere through a little muffler. And this is the symbol for a muffler, okay? If you take the literal drawing, it looks like air comes out of here, kind of hits a baffle, and it finally makes its way out. Okay, that's just the symbol. But they come in different shapes and sizes, but this is a very common one. This piece of brass on the end of it here is sintered, meaning it's very porous. You would know sintered from the oxygen stones that we use and the carb stones that we use when we're transferring the work into our fermenters. Okay, that creates those little micro bubbles. This sort of does the same thing. It takes the air and dissipates it through, distributes it through these little pores, and it muffles it because it's, as opposed to a big blast of air exiting into the atmosphere, it pushes it through there. It makes it much more quiet, a little bit more controlled. So, but this is a muffler, and that's just one more symbol on our drawing. Okay, so that is a shutoff valve, and sort of how that works. Okay, the next thing we're going to move into is these diamond-shaped type items that we're seeing in our schematic, and these condition our fluid. Now, when I say condition, it's not we're not adding anything to it or anything like that. Well, we could be, but actually, this is conditioning is basically, it could be filtration. Okay, it could be a filter. It could be a lubricator. Yes, that's where we would add something to it, because you still have actuators that require some lubrication on their seals so that they move freely. Okay, we don't want to flood a pneumatic system with oil, but very fine kind of mist sometimes, or maybe just a drop every 6-7 cycles or something like that. We want to maybe add some lubrication, but that's called conditioning, or possibly a dryer. You know, we live in the Ohio Valley, and our air is very humid. We're very humid in the summertime in particular, also the winter, but there's a lot of air in our, a lot of moisture in our air. That gets pulled into our compressed air system. So when you saw that compressor where we were pulling air from the atmosphere, compressing it, sending it on down the line, that water doesn't magically disappear just because it went through the compressor. Now it's just compressed and going on down the line, and you still have water in the system. Water and typically pneumatic devices don't get along, so in many cases you'll have to have a dryer, some type of a desiccant dryer that will retain the moisture and keep it pulled out, and then you'll have a cleaner, drier air going through your system. But my point is that the diamond shape here tells us, when we see it on the schematic, it's doing some kind of conditioning. Okay. And here's a host of different types of conditioning devices. We're not going to get into the ones that, particularly the ones that are involved with hydraulics. We're looking more at pneumatics. And so one of them might be a lubricator without a drain. Here's a lubricator with a drain. You'll say, here's the drain right here. This is without. Notice it doesn't have a little stem at the bottom of it. But here's the stem at the bottom, meaning that that lubricator has a water drain to it as well. I'm looking for, here's a cooler. You could run across a cooler in a pneumatic system, and also some type of a desiccant or a chemical dryer in the system. But notice that they all have in common, as far as conditioners are concerned, they are diamond shaped. So when you see those, you now know what you're looking at here. So these are, and it's also annotated with FIL01, filter 1, LUB01, lubricator 1. So my point is these are diamond shaped. And this filter here, your little stem on the bottom, that tells me that it's got a drain. So as it's filtering some water, if it gets too much water in here, we can open that drain and let that water out. Okay? But the diamond shape is what we're looking for. Now, we talked about the hand-operated shutoff valve. We know how that works. Over here on your valve body, you've got another shutoff valve, but it's actuated through a solenoid. Okay? Now, think back for a second when we were in the electrical part of our classes, and we took a solenoid. We had a solenoid coil. Okay. Now a solenoid coil is just simply one piece of wire wrapped around a gazillion times with a beginning and an end. One piece of wire, and when we wrap it around there, we put a voltage on there. We create a magnetic field. You should remember this from your electrical part of this class. So we create a magnetic field. Well, inside this spool, or this valve, is a spool, and when we put voltage on here and we create that magnetic field, it attracts that spool, or it could oppose that spool also. But we tend to attract that spool, and we pull that spool so that we shift the spool, and it provides different pathways for the air to go inside the valve body. We're going to get a little bit more into that in just a minute. Let's just take a quick look at this though. But here's our solenoid, okay? And these arrows mean pathways, okay? So and of course, there's the spring. This is a return spring. Now notice that there's no arrow, so we can't vary the tension on that spring. It's fixed, okay? So you got a solenoid on one side to move the valve body and a return spring to push it back into place once we de-energize this coil. We're going to get a little deeper into that. But these arrows represent the path of the air, depending on whether we're energized or de-energized. Okay. In this particular case, we're de-energized. The spring pressure is the dominant force, so it shoves this arrow block in place, and we have no pressure. We're not allowing our system pressure from our regulator. We're not allowing any pressure to go anywhere. It's stopped. It's deadheaded. It's blocked right there. Okay. However, the downstream pressure that we talked about that was still captivated, okay, we have a pathway to go out to our exhaust, out into our atmosphere. Now, if we were to shift this and put this set of blocks here, then our air would have a chance to come to our system, but this block would move over here and we would be blocking it from exhaust. In other words, we would be pressurizing our system up and not bleeding it off into the exhaust. We'll go into a little bit more detail here. Okay. Now this is a solenoid valve. This is a solenoid valve operated directional valve. Okay, shutoff valve. Excuse me. So what it is, this is the actual coil. Okay, and here's where we put our 24 volts, or it could be 120, depending on your control voltage. All right. So for this example, I just used 24 volts, okay? So we'll go through a little push button switch, and this is the start of the coil. There's the wire. It goes around and around a gazillion times, like I said earlier, and comes out the other side. We hook that to the neutral, that coil becomes energized, it shifts the valve, okay? So right now, the way we're set up here, we've got pressure from our system, but we're blocking it off because this set of arrows is in the valve. This is the position of the spool right here, so that it's blocking the incoming air. However, the air that's in the system that's already captured is there, right there, and it's exiting back into the exhaust. So you should have no air pressure at all because we've exhausted it all out into the atmosphere as it sits right now. Now, when I go to press my button, my push button, and I provide a path for the voltage to energize the coil, that magnetic field shifts that valve, okay? And when it shifts it, now the spool is allowing air to pass through the valve to our downstream system, all the other components we're going to deal with and we'll show you later. But it's going to allow it to go up here. And notice here, there is no pathway to exhaust. We're capturing and trapping all that air and moving it in our system, and we're not just sitting there dumping it to exhaust. We've blocked that port off. So now all of our system pressure is going to all the components that we're trying to control, okay? And control the components we're going to do in just a minute, okay? So when we de-energize, notice I've let my button off, we no longer have a magnetic field, okay? So the stronger pressure is in the spring. Let me show you too that when we do energize, that this coil, the magnetic field that shifts that spool, is stronger than the spring. So the spring gives way and lets it go. However, when we take our finger off the button and we no longer have that magnetic pull of the spool in our valve, then the spring pressure is the dominant pressure, it shoves it back in here, and now we've created a pathway that lets our pressurized air, we've blocked off the system air, now anything captured or trapped in our system goes to exhaust, and it's exhausted out into the atmosphere. But that is generally the difference between a hand-operated and solenoid-operated shutoff valve, and you saw both of those in the system, okay? So as I always like to do, just small snippets here, just chunks that you can digest. So kind of get your head around that for those who've never worked with them or seen them, you know, take time before we move into the next video. But the next one, we're going to talk a little bit more about some of our components downstream that we've kind of been building up to. For right now, just take a break, come on back, and watch the next installment, okay? Thanks a lot for watching, and we'll see you in a few minutes.